Hello class, so welcome to CHM 274, Practical Inorganic Chemistry. Today we shall begin by discussing qualitative analysis, after which we'll discuss quantitative analysis. So let's begin. First, I would like to revise some important topics with you before we go straight into the topic for today. You are expected to have known all this and you have been taught before, but because it will be very relevant in this course, I'll quickly highlight some of this important information. First, let's look at IUPAC nomenclature. Of course, you know IUPAC nomenclature is a standardized method of naming organic compounds and molecules. One of the major rules is that single atoms, anions are named with an "-ide" suffix. For example, if I have fluorine, I call it a fluoride. Once it is a single anion atom, we use a "-ide", that is a fluoride. If it's a bromine, that's a bromide, iodide, carbide, in that order. So what if the compound is a cation? The name of the compound is simply the cation's name, followed by the anion. For example, if I have a compound having a positive anion of calcium, positive cation of calcium reacting with a fluorine, and see it now, I'll call the positive atom alone, that is calcium, but for the fluorine being an anion, I'll call it fluoride. So that's calcium fluoride, calcium carbide, calcium iodide, calcium, arsenide, etc. Cations able to take on more than one positive charge are labeled with Roman numerals in parentheses. So if I have cations, that is positively charged atoms that are able to take up more than one positive form, that means they are able to have +2 oxidation states, +3 oxidation states, etc. For example, in copper can exist in the +1 oxidation state or in the +2 oxidation state. So I represent this by putting the number of charges in a parenthesis in the center. So if I was having a compound of copper and fluorine, which is supposed to give me a copper fluoride, it's possible for me to have a copper-1 fluoride or a copper-2 fluoride, depending on the ratio in which they are combining. So copper-1 fluoride is possible, copper-2 fluoride is possible. So to identify that, to show that disparity, we use this parenthesis showing the number of charge on the positive atom. An older outdated notation is to append OUS, which is HOS, or HIC, to the root of the Latin name to name ions with a lesser or greater charge. Upon this naming convention, Cu+ will be called cuprous, and Cu2+ will be called cupric. Don't mix this up. This is an outdated notation, so it is not necessary. We can just indicate it using the parentheses and the number. But in case you come across names like cuprous, it's just talking of copper in the +1 oxidation state, while cupric is talking of copper in the +2 oxidation state. Another important thing is oxyanions. When we have polyatomic anions containing oxygen, we call it a oxyanion. They are named using the IET or ATE suffix for a lesser or greater quantity of oxygen. For example, if I have a NO2-, it's called a nitrite because the number of oxygen is 2. When I have more oxygen, I call it a nitrate. So we call this kind of compounds oxyanion compounds. These are compounds that contain oxygen, is that okay? And the anion. You can see nitrogen there is an anion, is being combined with oxygen to form a oxyanion. And because the oxygen is more here, we call it nitrate. It is less here, we call it nitrite. Don't mix it up. CNO2 and NO3, they have different names. If 4 oxyanions are possible, the prefix will be hypo and par are used. The prefix hypo and par are used. So for example, if I have hypochlorite or if I have a perchlorate. So you can see if I have more than, you can see it's just one oxygen, so I call it the hypochlorite. And because this same compound can have a analog of ClO4 minus. We call this the perchlorate. So we use that to differentiate between them. Also, the prefix bi is an outdated way of indicating the presence of a single hydrogen ion, as in sodium bicarbonate. So it's not a very common way again, but it used to be the way it is being mentioned. Once I say sodium bicarbonate, that's your baking soda, NaHCO3. When there's hydrogen present in a molecule, we can just use the word bi. But the preferred method now is to name the hydrogen atom itself. So instead of saying sodium bicarbonate, it will be more appropriate for me to say sodium hydrogen carbonate. Also, we have the prefix CO, which indicates the substitution of oxygen by sulfur, so that we have a thiosulfate ion. Is a sulfate ion SO42 minus with one oxygen replaced by a sulfur, as in if we have S2O3. You can see SO4 here is the sulfate. This is a normal sulfate, but once I add a sulfur and I remove one oxygen and I have S2O3, I call it a thiosulfate. So that word thio simply signifies sulfur. Is that okay? Whenever we introduce sulfur to a compound, we introduce the word thio to indicate that sulfur. So the preferred IUPAC nomenclature for the protonated species of H2S2O3 is thiosulfuric acid. What happened here? You can remember H2SO4, is that not so? If I remove one of the oxygen in H2SO4, it becomes O3. And if I include one sulfur, it becomes H2S2O3. So we call this a thiosulfuric acid. Let's see some common names, ion names, some common ion names that we have. We have Cl minus for the monoatomic ions. We have Cl minus, that's chloride. S2 minus, that's sulfide. You can see they are anions, so we are using the ide, to signify them. They are always ending with the suffix ide. For P3 minus, we have phosphide. If I look at for my polyionic compounds now, for NH plus, I have ammonium. These are polyatomic now. They have more than one atom. I have ammonium, that's NH4 plus, sorry, NH4 plus. We have N3O plus, that is hydrozonium ion or hydronium. You can call it hydrozonium or hydronium. NO3 minus, we've mentioned that before, that's our nitrate. NO2 minus, that's our nitrite. ClO, that is our hypochlorite. Hypochlorite is a bleaching agent. Hypochlorite ClO minus. We have your ClO2 minus. Call that the chloride. Can you see the difference now? We are using the word hypo to signify that the number of oxygen is less in this. And then we have the one having your chloride. And then we'll have another one, which is your ClO3, which is even greater, which is called the chlorate. Okay, chloride, the chlorate. Then to show for the 4, I've told you before, we use what? Perchlorate. So we use the per to show greater number of oxygen from 3 to 4. And then to show that we have less than 2 oxygen from chloride, we have hypochlorite. Then SO3 2 minus, that's sulfite. SO2, SO4 2 minus, sulfate. HSO3 is our hydrogen sulfide. All these are important for you to commit to memory. There are many others that you can see here. So look at them properly. Just there are things you're already familiar with. Another important one you need to know is your CO3 2 minus carbonate. Very common, carbonate. If I have CrO4 2 minus, that's your what? Chromate. But if I have Cl2, that means if I increase the value of the chromium by 2, I'll have O7 2 minus, becomes dichromate. That's what we have in your K2Cl2O7, which is potassium dichromate, which is, of course, a dye and also used in test for many gases, which we'll see very soon. Okay, so let's proceed. Now, how do we name hydrates? If we have an hydrate, how do we name hydrates? The first thing is that hydrates are ionic compounds that have absorbed water. So when a compound absorbs water, we call it an hydrate. So any compound that has the ability of absorbing water, we call those the hydrophobic compounds. So those compounds, when they absorb the water, they form a new compound called an hydrate. they are named as the ionic compound followed by a numeric prefix and hydrate. Is that okay? The numerical prefix used are listed below. Let's see the numerical prefix. We can have what we call mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. All this represents number. Mono is 1, di is 2, and deca is 10 in that order. So for example, if I have copper sulfate and I have this hydrate, this 0.5 H2O is the hydrate. This copper sulfate has actually absorbed water. So this 0.5 H2O is representing the hydrate. So how do I call this? I name this first by saying this is a copper sulfate. But what is the oxidation state of copper here? I know sulfate, which is SO4, is supposed to carry a 2 minus. So therefore, copper must have a 2 plus. But if you don't know how to, go up, find it that way, you could just, solve it out any other way that is clearer to you. Another way to solve it out is to just say this is X. The oxidation state of sulfur is going to be -2. Oxygen is also going to be -2. Do the maths, and you are going to get that sulfur and copper here is also what? 2 plus. So the oxidation state of copper is 2 plus. So therefore, I'm going to say this is a copper 2 sulfate. After naming that, then I name the hydrate. How many water is this? 5. So I call this 5 is penta. Penta. Then I say pentahydrate. So this is a copper 2 sulfate pentahydrate. What of if there are acids we want to name? We want to name an acid. Acids are named by the anion they form when dissolved in water. If an acid forms an anion ending with "ide", then its name is formed by adding the prefix hydro to the anion's name and replacing the "ide" with "ic". Finally, the word acid is appended at the end of the name. So after writing the name, something "ic", and then I put acid. Let's see what I mean by that. For example, if I have what we call hydrochloric acid form, it forms a chloride ion with sulfur. However, the whole word is kept instead of the root, hydrosulfuric acid. Now let's see that in a more plain. Secondly, if we have anions with an "ate" suffix, they are formed when acid with an "ic" suffix are dissolved. E.g., if I have a chloric acid, which is my HClO3, dissolved into a chlorate, you can see the anion is having an "ate" suffix, chlorate anion, to form salts such as sodium chlorate. So you are going to be having a salt such as sodium chlorate. So the name will be called by the chlorate. You can see the acid in the first place here. We are calling it hydrosulfuric acid. Like your H2SO4, when you have a hydrochloric acid, forms a chloride ion. Is that not so? So because of that, if you react that with a sulfur, we call that hydrosulfuric acid. But for the other one here, I have a chloric acid dissolved in chlorate anion to form a salt called the sodium chlorate. So anions with the "ite" suffix, on the other hand, are formed with acid with an OUS suffix, are dissolved in water. E.g., if you have a chlorous acid is HClO2. If it dissociates it will dissociate into a chloride anion to form salts such as the sodium chloride. You can see it's just accordingly. This case is giving me a sodium chlorate, of course, because I'm using a chloric acid. And then this is giving me a sodium chloride because I'm using a chlorous acid. So let's see for oxyacid of chlorine. The 4 oxyacids of chlorine are called hypochlorous acid. Hypochlorous acid. Those are the 4 oxy acid of chlorine, and you can see them here. This is HClO, that's the hypochlorous acid. Second one is called the chlorous acid, which is your HClO2. The third is called the chloric acid, which is your HClO3, and the fourth one is a perchloric acid. You can see it still follows the same naming I told you. We use hypo to show that the oxygen is 1. We use ROS, OUS, to show 2 oxygen. We use RIC in this case to show 3 oxygen. But in the previous one, to show the 3 oxygen, it was rate, nitrate, to show 3 oxygen. But for the acids, we use the RIC, as chloric acid. Then perchloric to show another increase. The subprefix Pa is added to the chloric to show that another oxygen is included. So their respective conjugate bases are the hypochlorites. You know what we call a conjugate base? A conjugate base now is the base to which if I add it to this acid, it will neutralize the acid. So it's a conjugate base to this acid. For example, this one now is a conjugate base to this. This is a conjugate base to this. In that order, let me use a pointer so I can be clear. This here is a conjugate base to this. This is a conjugate base to this, in that order. So from here now, you can see HClO. Here it becomes ClO minus. So we call this a hypochlorite. You can see instead of the hypochlorous, now we're having a hypochlorite. Instead of the chlorous, we're having a chlorite. Instead of the chloric acid, we're having a chlorate. You can see now because it's an anion, so we're having a chlorate. And then for the last one, we also have a perchlorate. So I believe that's very clear. The corresponding potassium salt are potassium hypochlorite. So if I want to make a potassium salt of this now, all I just put is add potassium to the name. Potassium hydrochloride, potassium chloride, potassium chlorate, and potassium perchlorate. All that was added here is potassium. You can see it's already carrying a negative charge. So if I add a positive charge potassium, it will just marry it together. If I add the sodium, the same thing will happen. So I call this a sodium hydrochloride, sodium chloride, sodium chlorate, and sodium perchlorate in the same order. Now, oxyacids of sulfur, on the other hand, only the most common oxyacids are shown in this table. So there are many oxyacids of sulfur, more than what I have here. But these are the most common. I see sulfuric acid, H2SO4, that's our sulfuric acid. You can see your thiosulfuric acid. I've already mentioned that before. When we take off one oxygen and we add one sulfur, comes a thiosulfuric acid. Then your sulfurous acid is your, when you remove one oxygen, when you remove this H2SO3, when you remove one oxygen from the H2SO4, instead of calling it sulfuric, we call it the sulfurous. So those are the most common. Traditional naming, just for your information, I wouldn't be testing you on this. This is the traditional naming, the way it used to be named before the modern naming that we have already discussed already. When the metals has more than one possible ionic charge or oxidation number, the name becomes ambiguous. So when we have more than one oxidation number, the naming becomes ambiguous, becomes difficult to pin down the name of that particular compound. So in these cases, the oxidation number, the same as the charge of the metal ion, is represented by a Roman numeral in the parentheses immediately before the metal ion is named. So you can see in this case, uranium 4 fluoride, the oxidation number of uranium 6 fluoride, the oxidation number is going to be 6. The same thing, I can have ion 3 or ion 2, like I have here. This ion 2, this ion 3. Both of them, the parentheses represents the oxidation state of the metal. An older system uses prefix and suffix to indicate the oxidation number according to the following scheme. Let's see that. For example, if it's a cation, if it's the lowest form, we've already mentioned this before, we use hypo in front of it. If it's a cation that is positively charged, as it begins to increase from 1 to 2, we remove the hypo and we just call it by the name. If we have another one, we put a IC. If we have another one, we use a par IC. For example, let's put chloride here. This is a hypochlorous, this is a chlorous, this is a chloric, this is a perchloric, and this is a hyperchloric. But if it was a negative ion, for example, if it was negative and it was not a positive ion, I'll be having hypochlorite, a chlorite, a chlorate, a perchlorate, and a hyperchlorate. So you can see these same statements here are what we have been discussing before now. So, but instead of using this, we can also use a parenthesis to show the different oxidation state to make it clearer. But this is a traditional naming, which I've also explained before now. The system has partially fallen out of use, but survives in the common names of many chemical compounds. For example, ferric chloride, instead of calling it iron 3 chloride, people commonly call it ferric chloride. and potassium permanganate instead of potassium manganate 7. Potassium manganate 7 is the correct name, KMNO4, but people just call it potassium permanganate. So these names are still relevant, for some common names, but this is not the IUPAC name. The IUPAC name, you must use these numbers in parentheses. So that's the difference between the IUPAC and the traditional naming. Now, finally, on nomenclatures, let's see how to name complexes. I believe first semester you've already been taught how to name complexes. So, but I would also be mentioning it for the sake of this practical class. And you will be tested on it also. So this will be more like a bonus for you. Many of you already know how to do this very well. So when naming a complex ion, the ligands are named before the metal ion. Of course, you know what the ligand is and the metal ion. When we are forming a complex is formed between the metal ion, which is the central atom, and then the ligands. So let's see, how do we do it? First, you name the ligands before you name the metal. You write the name of the ligand in alphabetical order. So numerical prefix do not affect the order. So when I say numerical order, it does not include the prefix. For example, mono, tri, di, penta, hexa should not affect the prefix. What you would be arranging should not affect the order. What you'll be arranging is the ligand itself. For example, ethylene diamine should come before oxalate, irrespective of what prefix is in front of it, whether di, tri, tetra, penta, hexa, etc. Another important thing you should not forget is that when we are naming a bidentate, I believe you've already been taught all this, which I'm very sure you were taught this in first semester. So I believe you know what I mean when I say bidentate. Bidentate means that the ligand has more than one teeth. That's literally how to explain it. Is that its dentate is representing teeth there now. So it can attach itself to a metal ion in more than one way. So if it can attach itself in two ways, we call it bidentate, etc. So for example, ethylene diamine, oxalate, they are polydentate. It means they have more than two teeth. So because they are polydentate, when we want to name them, we don't use tri, di, tetra, penta. Instead, we use bis, tris, tetra, kis, etc. When we want to name bidentates or polydentate ligands. Anions end in IDO. This replaces the final E when the anion ends with it. Is that okay? Sulfate becomes sulfato. It replaces the IDE. Cyanide becomes cyanido. Is that okay? So, but for water, which are the common ones, is aqua or aquo. NH3, which is also very common, is your amine. Don't misspell this as AMINE. It is AMM, because AMINE, amine, has a different meaning entirely. That is NH2. Is that okay? But in this case, it's NH3, which is ammonia. We call it amine. H2O, which is water, we call it aqua or aquo. And then CO, we call that the carbonine. NO, we call that the nitroside. These are the important ones you need to know. Once you know this, you shouldn't be having problem naming them. Write the name of the central atom ion. If the complex is an anion, the central atom name will end with 8. So if the whole complex itself is an anion, that means carrying a negative charge. I mean the overall charge is negative. The overall charge is negative. This implies that at the end of that name, we will be adding a 8. For example, if the central metal is a ion, it will be ferrate. Is that okay? If it's a copper, it will be cuprate. So because it's an anion. But if it's not an anion, you write the original name. For example, if it's copper, you write copper. If it is iron, you write iron, not ferrate. You get what I'm saying now? So that is what that means. And its Latin name is used if available. That's in the case of iron that I said now. Instead of using ion, when it is anion, when it is a negatively charged complex, instead of saying ion, we say ferrate. That's the Latin name of ion. So if the central atom oxidation states need to be specified, you write it as a Roman numeral in parentheses. So if it is ion 2, you put 2 in the parentheses. If it's ion 3, you put 3 in the parentheses, etc. So you name cation, then anion as separate words. Let's see examples. These are common examples that you can be tested on. This is what you are very familiar with. This is NiCl4 2-. Let's name this before we see the answers. I would advise you right now to pause the video and give names to all these complexes, and then we solve them together. Okay, I'm assuming you have paused the video and you have played it back. So for the first one, the correct name will be tetrachloro. You can see we have the ligand here is chlorine, so we have to name the ligand first, and you name it with the prefix because there are 4 chlorine, so I call it the tetrachloro. Now, how many nickel do I have there? It's just 1 nickel. And what's the oxidation state of the nickel? Is the power here, which is 2-. The overall charge of this complex is negative. So therefore, it is a anion. And therefore, if I want to name the nickel, I'll call it a nickelate. So this is a tetrachlorido nickelate 2-ion. This is a tetrachlorido nickelate 2-ion. So this is the correct name for this. But if you name it tetrachloro nickelate 2-ion, you would also be correct. But you'll be most correct using the correct IUPAC naming if you call it chlorido, because it is an anion, which I've named, which I already explained in the previous slide. Okay, for the second one, which I know many of you find more difficult because we have more than one ligand here. Let's see how to name this. So let's start alphabetically. The first ligand here is amine. This second one is a chlorido. So which one do you name first? You name amine because amine starts with A. So you name that. Amine here now is just one of it, so I call it amine. But for chlorine now, there are 5 of it, so I call it pentachlorido. You can also see the overall charge of this complex is a negative charge. So it means that this copper is going to be negative. But how do I know the oxidation state of this copper? Don't mistake it and say the oxidation state of the copper is 3. No. To find the oxidation state of the copper, I'm going to calculate for the oxidation state of the copper. Let's calculate that together and determine the oxidation state of copper. Okay, so let's say copper is X. You can see amine here is a neutral ligand, so therefore it is 0. So I'll say X plus 0. It means a neutral ligand, so X plus 0 plus chlorine here is carrying a negative sign, is -1. So there are 5 of it, meaning 5 times -1, which is -5. So I have in bracket here -5. So all of this is equal to what? All of this is equals to -3. How do I know it's equals to -3? -3 is the charge, okay? You can see the charge here is -3. So I say all of this equals -3. So this becomes X plus 0, which is still X. Take -5 to the other side, it becomes +5. So this becomes 5. And what do I have on the other side before -3? That's +5 minus 3, which is equals to what? 2. So it means +2, which means the charge of copper here is +2. So therefore, if I want to name it, I say this is a amine pentachlorido cuprate 2-ion. Why am I calling it cuprate? It's because the overall charge of this complex is negative. So the overall complex is anionic in nature. So therefore, it is going to be having the name cuprate 2-ion. So that is how to give the correct naming. Okay, the next one. Now, in the case of this next one, which we're having cadmium, in case you don't know, CD is cadmium. So, but from here now, En represents ethylene diamine. And ethylene diamine is a polydentate ligand. It's not a monodentate ligand like amine, chloride, fluoride, water, and the rest of them. So because of that, when we want to name the bidentate, instead of saying tri, di, etc., we use, for 2, we use your bis. For 3, we use tris. For 4, we use tetrakis, and so on. So let's try that and see. This will therefore be dicyanide. Cyanide is a anion, so we call it cyanido. So we have a dicyanido. To name the ethylene diamine, because there are two of it, I say bis ethylene diamine cadmium 2. Now, why am I not saying cadmate, cadmate 2? I'm saying cadmium instead of cadmate here because the overall charge here is not negative. So this complex here is not a negative, it's not an anionic complex, it is positive. So therefore, the cadmium is plus. And you can see I'm not ending it with ion because there's no charge on top of this place. So I just call it cadmium. So how do I know cadmium has a charge of 2? Of course, we can also find that out from here. Ethylene diamine is a neutral ion, so this is 0. This one here is cyanide, which is Cn minus. The charge is -1. So -1 times 2 is -2. Take -2 to that side, become +2. So cadmium, we have a +2 oxidation state. So finally, the last one is a pentaamine chlorido-cobalt 2 sulfate. Now, you can see I'm having a counter ion outside, which is a sulfate. So you name this one last. After you have named this, the whole complex, you just add the one outside, which is sulfate. If what I have outside was a chlorine, I would have just say chloride in that order, just like you're having sodium chloride, sodium sulfate. So all this now has been reacted, married together with this anion to form this compound. So this is a pentaamine chlorido-cobalt 3 sulfate. So that's the correct naming for that. Let's quickly look at some solubility rules, and then we dive into our qualitative analysis fully. After which, the next video of making will be on quantitative analysis. So solubility rules, group 1 and all group 1 and ammonium compounds are soluble. So if I give you a set of compounds and I say which of the following compounds are soluble, once you see it's a compound of group 1, for example, sodium chloride, it has to be soluble because sodium belongs to group 1 of the periodic table. So, and all compounds of ammonia are also soluble. Okay, another one is nitrates. All nitrates and all chlorates are soluble. So if you say any compound that is a nitrate or a chlorate, they are all soluble. Acetates like ethanoates are also soluble, except from silver compounds. So if I have a silver acetate, it will still be insoluble because silver itself isn't soluble. So except from silver acetate, but all other ethanoates, acetates, ethanoates can have any ethanoate, sodium ethanoate, potassium ethanoate. Once you see ethanoate named there, it has to be soluble, except it is a silver ethanoate. Also, chloride, bromides, and iodides are soluble, except from their silver again, lead, copper, and mercury. Sulfates are also soluble, except from silver, lead, barium, cerium, and calcium. So you observe a trend here that all the compounds of silver are insoluble, irrespective of whether it's a sulfate or a nitrate. Even though we have nitrates and sulfates to be soluble, once it's a silver sulfate or lead sulfate, it will definitely be insoluble. But funny enough, also calcium, also sulfate, calcium sulfate is also insoluble. So take note of those exceptions. So let's see insoluble compounds. For the carbonates, all carbonates generally are insoluble, but except from group 1, you said that all group 1 are soluble before. So if you have any group 1 compound, whether it's carbonate or not, it will be soluble. If it's an ammonia compound, which we have said before, any ammonium compound will be soluble. And if it's a uranium compound, that means uranium is a uranium compound, it will be what? Soluble. We have a sulfite. All sulfites are insoluble, except from group 1 again and ammonium compound. Wherever you see group 1 and ammonium, they are always the exceptions because they are always soluble. Phosphates are insoluble, except from group 1 and ammonium. Hydroxide and oxide are insoluble, except from group 1 and ammonium. And then some others, just make sure you know group 1 and ammonium. Those are the ones that I would most likely put as tricks so that you can be able to find out that indeed it is insoluble or soluble. Sulfites, can see there's difference between sulfate and sulfite. This is sulfate, SO3. This is sulfite, SO2. Is that okay? So this the sulfate, this is the sulfite. And then except from group 1, group 2, and ammonia compounds. Then chromates also, all chromates are insoluble except from that of sodium, potassium, and if you observe, you see these are also group 1 compounds, group 1, sodium and potassium are in group 1. So all group 1 chromates are soluble because we've said all group 1 are soluble, all group 1 compounds are soluble earlier. Also for ammonia, you can see this is an ammonia compound, an ammonia chromate, which will also be what? Soluble. And then interestingly, magnesium, though it's in group 2, is also soluble. So those are the things you need to put in mind as regarding solubility. Now let's look at safety in the laboratory, which is very important. Let's just look at some precautionary measures that are taken in the laboratory before we go. Let's look at safe handling of acids and base. There are a number of proper procedures for the safe handling of acids and bases that you need to know because you'll be working on them. You know, if we're allowed, if not for the prevailing circumstances, we're supposed to have some practical sessions where we work on some inorganic compounds to carry out some qualitative analysis. But due to the constraints, we will not be able to do that for this course, but other subsequent courses you'll be having, you have to go to the laboratory, so you have to ensure you know these precautions. So I'll be testing you on these precautions since we are not able to have a laboratory practical. So let's see, both acid and bases can be corrosive to human tissues. So you need to know that it's not only acids that are corrosive. Both acid and bases can be corrosive. All it depends on their concentration. So the more the concentration, the more the dangerous those particular substances become. So you must be particularly careful about getting them in your eyes or even in your stomach. So taking in base can be, neutralized by taking in a lot of water. You can flush it out with a lot of water, or if it's acid on your hand, you can flush it with a lot of water to neutralize the acid. So also, you are supposed to get some acid or base on you. Suppose you get some acid or base on you, other than in your eyes, the procedure is essentially the same. Just use a lot of water to flush it out, except it is in your eyes, because it is very, very dangerous to have it on your eyes. If it's on your eyes, then you need to take up some more precautionary measures than just washing it with water. If you have spilled acid or base on the lab bench or on the floor, treat it immediately. It is an acid, first neutralize it with sufficient sodium hydrogen carbonate, commonly known as baking soda. We have a spill kit. You can use a spill kit available. So just ensure you request for these things when you are in the laboratory. When you have acid poured on a bench, you request for sodium hydrogen carbonate. Why do I need sodium hydrogen carbonate? It's because it is a base. If I react a acid with a base, it will form a salt. So automatically it changes the acid into a salt, and I can easily sweep it off my table without having anything to fear. The quantity and concentration of acid and base used in the exercise are permissible to flush down the drain. So if we're supposed to have this practical, whatsoever quantity of acid or base you'll be given will be the one that we can easily flush down the drain. Let's look at some hazard warning symbols. If I see a symbol like this in the laboratory, it is telling me that this substance provides oxygen, which allows other materials to burn fiercely. So it means that substance is oxidizing. If you see this symbol here, it means it is harmful. If you see this symbol, it means penetrating radiation. That means it is carcinogenic. It can cause cancer. So these are symbols you should watch out for in the laboratory. This signifies highly flammable. This signifies corrosive. That means it can burn. That is commonly an acid. This very unstable form and gas fast. If you have this sign, very similar to the harmful, but you have I, it means it's an irritant. These substances are not corrosive, but they can cause reddening or blistering of the skin. Then, if you see this cause sign, it means it is toxic. In most chemical bottles, like your H2S, that's hydrogen sulfide, you see this, this sign here, which is showing you that it is toxic, and it's possible for such substance to cause death. So please ensure that you watch out for this. Now, if you have most corrosive substance, remember they are acids, and remember the triple A, always add acid to water, never the other way around. We always add acid to water and not water to acid. The reason why we do that is because when you add water to acid, it will be explosive. Why? Because a little water will have to react with so many acids initially, and hence the reaction will be spontaneous and will be very, very exothermic in nature and cause an explosion. But if you add acid to water, the reaction will be endothermic, and as a result, it will go in smoothly without any problem. So always remember that. So now let's settle into our qualitative inorganic analysis. We'll just be looking at a very few analysis on qualitative inorganic compounds, and then we'll be done with this part of the course, and then we'll have just the quantitative analysis left. Now let's look at what we call non-oxidizing acids. Non-oxidizing acids. They are also known as inorganic acids or mineral acids and include hydrochloric acid, nitric acid, phosphoric acid, sulfuric acid, boric acid, hydrofluoric acid, and hydrobromic acid. All these, we call them organic acid or mineral acid. You can see nitric acid I put here, dilute. They are in the diluted form. Sulfuric acid, dilute. So we call them the mineral acid. Inorganic acids are generally soluble in water with the release of hydrogen ions. The resulting solution have pHs that are less than 7. So, of course, they are acidic, so they must have pH that are less than 7, and they are generally soluble in water. They are generally soluble in water. Acids neutralize chemical bases. For example, amine and inorganic hydroxide to form salt. So whenever you have an acid reacting with a base, it will form salt. Neutralization occurs as the base accepts hydrogen ion that the acid donates. Of course, that's your popular neutralization reaction. And neutralization can generate dangerously large amount of heat in small space. The dissolution of acid in water or the dissolution of their concentrated solution with additional water may generate sufficient heat. So the addition of water often generates sufficient heat in the small region of mixing to cause some of the water to boil explosively, resulting in bumping, spatters, or spatters of the acid. So that's why I was saying that you should not add the water into the acid because it will explode. It will generate so much heat and it will explode. So we add the acid instead into the water. So these materials react with active metals, including structural metals as aluminum and iron, to release hydrogen, which is a flammable gas. Now let's see some very, very important tests, qualitative tests for gases. When we say qualitative, we are talking about what is present. We want to know what is present in a particular sample of a substance. So quantitative is how much of it is present. So now is qualitative. How do I know that hydrogen is present in a particular solution? We test hydrogen using what we call a lighted splint. And what happens is that it will give a pump sound. When you put hydrogen, is like a fire, a lighted splint. Once you put it near where hydrogen gas is, you hear a pop sound. Once you hear a pop sound, it is confirmation that hydrogen is present. What of oxygen? We test it using what we call a glowing splint. When you set the glowing splint on fire for a few seconds, you allow it to off. It is still hot, but you allow it to off. Once it's off and you bring it near oxygen gas, it will reignite the glowing splint. So it will bring back the fire immediately because, you know, of course, oxygen supports combustion. So once it reignites the glowing splint, it is a proof that that gas has to be what? Oxygen. Out of CO2, how do I test for carbon dioxide? I just bring a lime water. If I pass CO2 into a lime water, the lime water will turn milky. So it changes the lime water into a milky solution. So it proves to me that it has to be what? CO2. How do I test for hydrogen chloride? I can use a moist blue litmus paper. Since hydrogen chloride is, hydrochloric acid is an acid, if I put it near a moist litmus paper, it will turn it from blue to red. What of ammonia? Ammonia is a base, so if I put a red litmus paper, it will turn it from red to blue. SO2, which is sodium dioxide, your sodium dioxide, sulfur dioxide. If I put it with a moist dichromate paper, it will change the color from orange to green. So there will be a color change from orange to green. What of chloride? I want to measure chlorine gas chlorine gas, all I need to do is a drop of silver nitrate. So if I put a drop of silver nitrate on that particular solution that I'm suspecting chlorine gas to be present, it will give me a white precipitate. A white precipitate will be formed. What of for bromine gas? The same drop of silver nitrate is used. It will give a cream precipitate. Then for NO2 or NO, both of them, they have a quite ambiguous way of testing them. All we do is just put that particular substance in water. If you put it in water, it will produce a orange-brown gas. That's for NO2. But if I put the NO gas in water, it will move from a colorless solution to a orange-brown gas. So that proves to me that it has to be what? NO2. Now for the last one here, which is hydrogen sulfide, H2S, you use a moist lead ethanoate, which is now called acetate. Instead of calling it ethanoate, I'm going to call it an acetate. Moist lead acetate paper. It will give me a rotten egg smell. So that is how we test for these popular gases. Let's see basic oxides and hydroxides. Basic oxides and hydroxide. A basic oxide is an oxide that shows basic properties in opposition to acidic oxide. Don't say something is a basic oxide, it shows properties of a base, which is different from that of what? Acid. And basic oxide either react with water to form a base, or they react with acid to form a salt. So I can use that to know that a particular oxide is basic once it reacts with water to give me a base, or it reacts with acid to give me a salt. Let's see examples. Sodium oxide, which can react with water to produce sodium hydroxide, which is a base. So therefore, it means sodium oxide has to be a basic oxide. Magnesium oxide, which reacts with hydrochloric acid to form magnesium chloride. You can see it has to be a basic oxide because it has reacted with an acid to form a salt. Copper oxide, which reacts with nitric acid to form copper nitrate. You can see it reacts with an acid to form a salt. Basic oxide are oxide mostly of metals, especially alkali and alkali earth metals. That's group 1 and group 2 metals. Now we also have the ones we refer to as the amphoteric oxide. Amphoteric oxide, they are not basic, but they can react as base and acid at the same time. So sometimes they react as base, sometimes they react as acid, so we call them amphoteric oxide. So an amphoteric substance is a compound that can react as an acid and as well as a base. The word is from a Greek word amphoterio, which means both. So many metals such as zinc, tin, lead, aluminum, beryllium, and most metalloids have amphoteric oxide or hydroxide. So amphoteric substance can either donate or accept a proton. So they can either act as an acid or as a base. Now, look at these very important examples that I'll be giving you, which are the ones that we'll be sticking with. There are many and many of them, but for the case of this, for the purpose of this class, we'll be sticking to these few. Zinc oxide reacts differently depending on the pH. That means zinc oxide can react as a acid or as a base. For example, if it's in an acid, which is a low pH, zinc oxide reacting with any acid, let's say we have H plus now representing any of the acid, it becomes zinc 2 plus plus H2. So if H plus here was to be 2H2SO4, it should have moved from zinc to zinc sulfate, that's zinc SO4, and then plus water. If it reacts with a base here, which is zinc oxide reacting with NaOH, zinc oxide reacting with NaOH, it gives me a Na2ZNO2 plus H2O. So it reacts with a base differently from the way it reacts with an acid. So this effect can be used to separate different cations such as zinc from manganese. So because of the property of zinc to act both as an acid and as a base, it is a very important property that we use in the laboratory to separate out different cations such as zinc and manganese. Okay, so let's see. Another one is aluminum hydroxide. Also is an amphoteric oxide, can act as an acid and a base, and these are the corresponding equations. make sure you go through them. Then also some other examples that we have of amphoteric oxide is aluminum oxide. These are nitroxide, so this is aluminum oxide, and then lead oxide, among others. So just commit those to memory. Oxidizing acids. So let's quickly look at oxidizing acids. Now, an oxidizing acid is a brusted acid that is also a strong oxidizing agent. Now, the word brusted here is the name of a scientist. Brusted was defined the acids as proton donators. So you can say an oxidizing acid is a brusted acid that is also a strong oxidizing agent. All brusted acid can act as moderately strong oxidizing agent because the acidic proton can be reduced to hydrogen gas. However, some acids contain other structures that act as stronger oxidizing agent than hydrogen. Generally, they contain oxygen in the anionic structure. So these kind of compounds include the nitric acid, perchloric, chloric, chromic, and concentrated sulfuric acid, among others. So for example, copper metal cannot be oxidized by and dissolved in a non-oxidizing acid because it is lower on the reactivity series than acidic hydrogen. However, an oxidizing acid such as nitric acid can oxidize the copper and allow it to dissolve. So let's see some of these oxidizing acids, and then we'll conclude from there. So nitric acid now is a strong electropositive metal, such as magnesium reacts with nitric acid as with other acid, reducing the hydrogen ion. So it's possible for magnesium to react with H2, H plus, can say it's strongly oxidizing metal. So it's magnesium reacts with the nitric acid as with other acid, reducing the hydrogen ion. So this is just a simple equation. Mg plus 2H plus will just give you your 2mgh, 2mgh. So with less electropositive metal, the product depends on temperature and the acid concentration. For example, copper reacts with dilute nitric acid at ambient temperature with a 3:8 stoichiometry. So we can see the 3:8 stoichiometry here with Cu, which is cobalt, reacting with nitric acid at ambient temperature. I expect you to balance these equations yourself. I've been giving you the value for most of the equations before now. So try to work on those equations. Very important. The nitric oxide produced by may react with atmospheric oxygen to give nitrogen dioxide. So put that in mind. Passivation, let's see, although chromium, iron, and aluminum readily dissolve in the dilute nitric acid, the concentrated acid forms a metal oxide layer that protects the metal from further oxidation, which is what we call the passivative. So even though it's readily dissolved in dilute acid, these metals readily dissolve in dilute acid, the concentrated acid form a metal oxide layer that protects the metal from further oxidation. So it would not be able to, to be oxidized by any of these metals, because these metals are forming what we call a protective coating around themselves. So we call that passivation. Sulfuric acid. Sulfuric acid reacts with most bases to give the corresponding sulfate. For example, blue copper salt, copper 2 sulfate is prepared by the reaction of copper 2 oxide with sulfuric acid. So of course, you can easily supply the product to this. Can say I've already given you an hint already. The blue copper salt, which is your copper 2 sulfate. All that happens here is that copper will react with the sulfates to give you CuSO4 plus H2O. So the product will be CuSO4 plus H2O. Sulfuric acid can also be used to displace weaker acids from their salt. Reaction with sodium acetate, for example, displaces acetic acid, CH3COH, and forms sodium hydrogen sulfate. So what will be formed here is sodium hydrogen sulfate, which is Sodium here will come here. One of the hydrogen comes to this place to give you CH3COOH, which is this. And then the remaining one hydrogen here, sodium comes to replace it. It becomes sodium hydrogen sulfate with CH3COOH, which is your acetic acid. Similarly, reacting sulfuric acid with potassium nitrate can be used to produce nitric acid and potassium hydrogen sulfate. Concentrated sulfuric acid reacts with sodium chloride and gives hydrogen chloride gas and sodium hydrogen sulfate accordingly. So this is the equation. When a concentrated sulfuric acid reacts with sodium chloride, it will give you a hydrogen chloride gas. That means hydrogen reacting with this as HCl and a sodium hydrogen sulfate. So NaHSO4. So those will be the corresponding product. Similarly with other halide salts. So it means we can also have sulfuric acid reacting with other salts of the halogens. So finally, sulfuric acid reacts with most metal via a single displacement reaction to produce hydrogen gas, and the metal sulfate dilutes H2SO4, attack iron, aluminum, zinc, manganese, magnesium, and nickel. So, but reaction with tin and copper require the acid to be hot and concentrated. So you see some reaction, they'll tell you hot sulfuric acid. So sulfuric acid sometimes, in order to react with metals like tin and copper, it must be hot and concentrated. So lead and tungsten, however, are resistant to sulfuric acid. The reaction with iron shown below is typical for most of these metals, but the reaction with tin produces sulfur dioxide rather than hydrogen. So you can see the reaction here that was shown with iron. Iron can react with H2SO4 to give you a iron sulfate plus hydrogen gas. So hydrogen gas will be evolved when you react to give you the iron sulfide plus hydrogen gas. The same thing will happen here. SN is tin. Tin reacts with this, will give you a tin sulfide plus hydrogen gas. The reaction may be taken as typical. The hot concentrated acid generally acts as an oxidizing agent, whereas the dilute acid acts as a typical acid. So that is where we are going to be drawing the curtain for the qualitative analysis. The major things that you need to commit to memory here and study properly is those what we revised on IUPAC nomenclature, naming of complexes, solubility, and then the few compounds we took on the few inorganic compounds we took. That's your nitric acid, sulfuric acid, then amphoteric oxide and basic oxide. Just pick some of those examples I give you and understand them properly. Those are the things I'll be testing you on with regards to this. And finally, we'll look at qualitative analysis in the next video. So thank you very much.